So last class we talked about mirrors and images of objects that are formed by mirrors. And today's class I want to talk about lenses and the images of objects that are formed by lenses. We're going to talk about two specific situations. One in which an image is formed by refraction at a single flat planar surface. So an example of that might be when you look in a fish tank and see the fish. You're seeing an image of the fish. So that's one case we'll look at. The other example we'll look at is image formed by lenses where you have refraction at two surfaces, bending of light rays at two surfaces. So when the light goes into the lens, when the light comes out of the lens. We'll look at that example of images formed by refraction. As we work through the examples today, we'll both be drawing or sketching, ray tracing the images of the objects and looking at their properties. And we'll also be calculating, computing with equations the properties of the image and the nature of the image. A lot of what we do today will be similar to what we did in the last class. The ray tracing is very similar to what we did in the last class with mirrors. The equations we'll use are very similar to what we used in the last class. So this class is really building on the last class. As I mentioned before, the use of lenses and the use of mirrors to make images of objects was literally the birth of modern biology. It's how microscopes got built. It was the birth of modern astronomy. It's how telescopes got built. So what we did last class with mirrors, what we do today's class with lenses, opened up these new unseen worlds and led to modern astronomy and biology. Everything in today's class is built on the law of refraction, like everything in the last class was built on the law of reflection. So I just wanted to start with a reminder of the law of refraction. Like the last class, we started with a reminder of the law of reflection. So here's the law of refraction. So refraction, remember, is the bending of light when it travels from one medium, one optical medium, to another optical medium. And here we're picturing the refraction of light, and here I've written down the equation for the refraction of light. So in the picture, upstairs here above the horizontal line is one optical medium. Maybe a good example for today's class is this is air. And then downstairs here below the horizontal line is another optical medium. A good example for this class would be glass. These two media, say the air and the glass, are characterized by two refractive indices that describe their optical properties. So I've labeled them the refractive index N for the incident medium and the refractive index R for the refracted medium. And then when the light crosses the boundary between the two medium, it's deflected, it's bent, it's refracted, and it's bent, refracted, deflected according to this rule here, this law here. This is Snell's law. And that law says that if you take the product of the refractive index and the sine of the incident angle, and you take the product of the refractive index in the second medium and the sine of the refracted angle, those two products are equal to one another. That's the law of refraction. If you want to think about the law of refraction and how it's working, you might want to think, imagine I'm a lifeguard, which is a ridiculous thought, but imagine I'm a lifeguard. And supposing I'm hanging out on the beach and there's somebody I notice that's drowning in the water. So I'm going to, ridiculous thought again, save this person in the water. How am I going to get from where I am on the beach to the person in the water? Am I simply going to go in a straight line from where I am now on the beach to where the person is in the water? No, because I'm a lifeguard, and I'm trained that I can run faster on the sand than I can swim in the water. So actually the route that light takes, like the route that the lifeguard takes, is the shortest path in time. It's not the shortest path in distance, it's the shortest path in time between the point that I start at and the point that I end up with. So I'm going to run further on the sand because I can run faster than I can swim. I'm going to swim less in the water because I swim slower than I can run. That way I get to the person I'm trying to save as fast as possible, and that's what light does, and that's what this law of refraction dictates. It's the fastest path from P to Q. The light travels faster in the lower refractive index medium. The light travels slower in the higher refractive medium. The light is getting from P to Q as fast as possible. That's actually the basis of this law. Okay. I'm up to date. I'm actually not up to date in anything, so it's ridiculous that it tells me. I'm completely un-up to date. Okay. Let's look at the first case, which is refraction by a single surface, and it's just going to be a flat surface, what we would call a planar surface. And so here's a picture of that situation. I'm going to just show you some rays so we can construct the image of the object in this situation. Then I've got another slide, which is where I'll show you the equations for refraction at a single planar surface. So we've got some equations for it, and then we'll look at an example. But let's start with this case. Over here on the right-hand side, let's imagine that this is water in blue. And over here on the left-hand side, let's imagine that this is air in this white color here. And we'll imagine maybe that so here's my eye, I'm looking at a fish in a fish tank. So when I look at the fish in the fish tank, the fish is the object, and I observe the image of that object. And so let's trace some of the rays from the fish to my eye, and in that way construct the image of the object. I'm just going to draw a couple of rays on this sketch. So this horizontal line is again the optical axis. So it's perpendicular to the boundary between the two media. It's right angles 90 degrees to this vertical boundary. On this picture is the object in green here. So this is the fish, see? And then also on this object, this is what we're going to construct, is the image of the fish that I see. And it's in magenta here. I labeled it I. And again, we'll use this language. I'm using this language as P is the object distance from the boundary between the two surfaces here, and Q is the image distance from the boundary between the two surfaces here. So I'm going to trace two rays so that we can figure out where the image of the object is located. And I can just do two rays on this simple sketch of a refraction at a planar surface. One ray is this horizontal ray that's going from the right to the left here. And then the second ray is this ray that's also going from the right to the left, but it's also going up, and it's getting refracted here. So let's first just walk through each of those rays and then trace back where the image that I see based on those rays is located. So the simple one is this ray here, this horizontal ray here. It's going parallel to the optical axis. It strikes the boundary between the two media, between the water and the air, it strikes that boundary at an incident angle of 0 degrees. So the incident angle is 0 degrees. The refracted angle, this is a special case of refraction. If you strike at an incident angle of 0 degrees, the refracted angle is actually 0 degrees also. So for this special case, when you strike the boundary at right angles to the boundary, then there's no bending of the light rays, and the light ray just goes straight through. So this is one ray that we construct here. The second ray that you can construct, well, a second ray, is this one going upstairs here. So this ray also travels from the fin of the shark, or whatever it is, up towards the boundary here. It strikes the boundary here. Now it's striking the boundary at a non-zero incident angle. And because it's traveling from higher refractive index to lower refractive index, it's going to be refracted away from the normal, so it's bent at a greater angle towards the normal. So this is the refracted angle here. And this is the law of refraction. This is Snell's law of refraction. And so this ray upstairs here, this ray downstairs here, these are two sample rays that are emerging from the air, from the water-air boundary. Of course, there's many, many rays, and I'm not going to draw all the rays. There's millions, thousands, billions of rays, but we just need a picture two of them to imagine the image. So here's my eye. I see these two rays. Here's my brain. I construct the image based on those rays, and I construct the image by seeing what's the common point those rays appear to come from. The common point, well, if I trace this one back, it comes this way. Trace this one back, goes this way. They cross here. This is the common point, and this is where the image is formed. And so this is how I located the image. And if you look at that image, it has a couple of interesting properties. So one is this image is closer to the boundary between the two media than the object was located. And that's true if you're looking into a medium of higher refractive index, like you're looking into a fish tank. It's also, you can see from the sketch, the same size as the original object. And that's true when you have an image formed by a planar surface. So already from our sketch, we've figured out some of the basic properties of the image formed by a planar surface. If the light is coming from higher refractive index to lower refractive index, the image is moved closer to the boundary. If it was the reverse, actually, we haven't sketched it, but if you went from lower refractive index to higher refractive index, the image is moved further away from the boundary. But in either case, the image size is the same as the object size. The magnification is what we would call 1. And so we've learned all that from our ray tracing here. Let me just make a couple of comments here about sort of language that we use for refraction at a single planar surface, conventions that we use for refraction at a single planar surface. Where the light came from, that was the front side. You can see I labeled it here. Where the light is going to, that's the back side over here. I don't know what this E is. This side, if the object is on this side, that would be a positive object distance. If the image were on this side, this would be a positive image distance. And so that's our convention. That's our language for positive objects are on the front side. Their locations are on the front side. Positive positions for the image would be on the back side. This is exactly the same picture. And out of this picture, you can actually, with a little bit of geometry, a little bit of trigonometry, derive equations for the image position, derive equations for the magnification of the image. I'm not going to explain it. It's just based on these two triangles here. the image position Q for single refraction at a flat surface is equal to the object position times this factor, a minus sign, and then the ratio of the two refractive indices. N1 is where the light came from. It was the front side. N2 is where the light is going. It's the back side. So this equation tells you the image position in terms of the object position and the media, and the two different media that the light has passed through. This is the equation for the magnification. Well, we already figured out the magnification, which is the relative size of the image and the object, was 1. And that magnification is 1, always 1, for this planar single refraction. It's actually plus 1, the plus sign indicating that the image is the same way up as the object. So that's what the plus sign means. Okay. Let's look at an example. I have one very strong memory from my childhood of my mum telling me over and over again, the water is deeper than it looks, like I'm suddenly going to jump in. So the water is deeper than it looks, and this is an example of the water being deeper than it looks. I.e., the surface, the water floor being closer than it actually is. So let's take a look at this example. So here we are at the beach again, and I'm looking in the water, and I see this shark. And I'm 0.5 meters above the surface of the water, and the shark is 0.5 meters below the surface of the water. And what we're actually going to compute, we're going to compute two things. We're going to figure out how deep I see the shark as being, the apparent depth of the shark. So that's the location of the image of the shark. We're going to figure out where I see the image of the shark. And we're also going to figure out, imagine that the shark is looking at me, dinner, and the shark is looking at me and saying, where am I? Does the shark see my image? So in my case, I'm looking at the shark. The shark is in the higher refractive index medium, and I'm in the lower refractive index medium. So the light is coming from higher refractive index to lower refractive index. For the shark, it's the reverse, right? The shark is looking at me. I'm in the lower refractive index medium. The shark's in the higher refractive index medium. So my light from me is going from lower refractive index to higher refractive index. And so we're going to look at those two cases of light going in the opposite direction from shark to me or me to shark, and the image formation in those two different directions. I think I'm going to work this out on the device I don't know the name of. So here we are. I've started it off a little bit. The shark is down here. I'm up here. The horizontal line is the boundary between the water and the air. Here are the refractive indices of air, essentially 1 for air, and 1.33 for water. Here's the distance, 0.5 meters, that the shark is truly below the surface of the water. Here's the distance, 0.5 meters, that I'm truly above the surface water. And we want to figure out where I see the shark's image and where the shark sees my image. I'll do mine first. So let's see. What am I doing? Good question. I look at shark. So this is what I'm going to solve first. Me looking at the shark. In that case, the medium, the first medium, that's where the light is coming from. That's what we're going to call N1. That medium is water, so that has a refractive index of 1.33. The medium where the light is going to, that's the air. That's N2, what we call N2, and that's it's 1.0003. I'll just write it as 1.00. It's close to 1. The object position, well, this is the position of the shark beneath the surface of the water. That object position, we call that P, and it's a distance that's 0.5 meters below the surface of the water. And it's positive 0.5 meters because that shark object is on the front side of this boundary. And so this is, I didn't write the plus here, but this is plus 0.5 meters. So that's the information that I know, and I want to figure out the image position. That's Q, and we wrote down an equation for the image position. It had a minus sign, and I'm laughing to myself because I've written it down wrong here. It had a factor of the two refractive indices, the backside refractive index divided by the front side refractive index, so that's N2 over N1, times the object position. Well, look, over on the right-hand side of this equation, we know everything there. We know the object position at 0.5 meters. We know the two refractive indices, and so we can just plug in all these numbers. So N2 is 1. N1 is 1.33. P is 0.5 meters plus 0.5 meters. And so if I multiply these things together, I get the image position. It's going to be, there's going to be a minus sign, and it's going to be 37 meters. And so that's where I see the shark's image. So I see the shark's image somewhere around here in this picture. Here's the shark. And so that shark's image is closer than the shark really is, because that's the nature of an image formed when you look into something that has a higher refractive index. But it has the same size as the original shark. The magnification is 1. Okay, now let's imagine that the shark is looking at me. So now the shark is looking at me. And in this situation, so the light is starting from me in the air. So the front side refractive index is 1. The back side refractive index, where the light is going, that's the water, that's 1.33. And the object position, now that's my position with respect to the boundary, that's also going to be this plus 0.5 meters. I was the same height above the water that the shark was below the water, so 0.5 meters. That's all the information I know. And now I can just go ahead and calculate the image distance. This is now the shark's image of me by this same equation. Remember, it's a minus sign. It's the ratio of the two refractive indices times the object position. All of these numbers I know. I've just written them down. I've just got to divide N2, 1.33, by 1 and multiply the object position by that. And if I do that, I get a 0.67. 0.67 meters. Look, this time we had the ratio of the water's refractive index to the air's refractive index rather than the air's to the water's. So this time the shark is seeing me as further away. I'm up here, which is off the screen. I'm further away, and that's the property of the image formed when you have light traveling from lower refractive index to higher refractive index. Okay. So that's why the water is deeper than it looks, right? The sand below the water appears closer than the sand actually is, just like the shark appears closer than the shark actually is. This also applies, that aliens are closer than you think. They are closer than you think in a physics sense. The shark was looking from the water of high refractive index out at a world of lower refractive index, and things looked further away than they actually were. Well, we're doing the same. We're down here on Earth, minding our own business, looking out through the atmosphere. Well, we're looking out through the atmosphere into empty space. We're looking from higher refractive index into lower refractive index. So not sharks, aliens out there in empty space will actually look further away than they actually are. Only by a little bit, but in the physics sense, aliens truly are closer than they look when you look out the atmosphere and see them. Okay. Let's start the second topic, which is the images formed by lenses. This is just to show you a little bit and introduce a little bit of language for lenses. There are two types of lenses, basically. And now the slide's moved off the screen. But anyway, there's upstairs here, these are all converging lenses. These are sketches of converging lenses. And downstairs here, these are all diverging lenses. So converging lenses, when the light passes through a converging lens, it gets bent towards the optical axis. That's what we mean by a converging lens. A diverging lens, when light passes through a diverging lens, that means that the light is diverged, bent away from the optical axis. So those are the two types of lenses, converging, diverging lenses, just like they were converging, diverging mirrors. The traditional, the sort of classic converging lens looks like this. It's wide in the middle, in the center, and it's thin on the outside. The classic, the traditional diverging lens is the opposite. It's narrow in the center, and it's wide on the outside here. So this is what we always think of as a converging lens. This is a type of lens that's thicker in the middle, that bends light towards the optical axis. This is what we always think of as a diverging lens. It's a lens that bends the light away from the optical axis. It's thinner in the middle and thicker at the edges. Again, when light passes through either of these lenses, there's two boundaries. The light passes from air into glass and then glass into the air. Likewise down here, air into glass, glass into the air. So there's two refractions, there's two reflections, there's two bending of the light rays. And that's how the lenses work to create an image from an object. Okay. You have a personality, I have a personality, and even lenses have a simple personality. So the lens personality I don't know what the ocean is, the human personality, but I don't know what any of the letters stand for. For a lens, there's just a very simple personality, which is its focal length. So firstly, focal length has one aspect of simply whether it's diverging or converging. So a converging lens is a positive focal length. A diverging lens is a negative focal length. And then the other aspect of the personality is the lens is how converging is it? Or how diverging is it? So if you've got a converging lens and it quickly converges the light, that's a small focal length lens. If you've got a converging lens and it just gradually converges the light, that's a long focal length lens. Likewise for diverging. If you've got a diverging lens and it very quickly bends the light away from the optical axis, that's a small negative focal length diverging lens. If it just gradually bent the light away from the optical axis, then that's a long negative focal length diverging lens. So with lenses, it's all about their characteristic, their personality is all determined by their focal length, its sign and its size. Here you can see on this little sketch and on these pictures here, one way of actually quickly seeing the personality of the focal length of a lens. What you do is you shine parallel light rays into the lens, and you'll see its focal length because the light rays are either bent to a location, that is the focal length, in the case of a converging lens, or they're bent away and appear to come from a common point, which is the case of a diverging lens. So if you look in this picture here, this is a real picture, a real light rays striking a real converging lens. All these parallel light rays are brought to this point here, pass through this point here. This is the focal length of this lens, the distance from the lens to this point. So we're literally seeing it. Over here on the downstairs here, we see parallel light rays, again, real parallel light rays. There, it's a little hard to see, but they're hitting a diverging lens. It's thinner in the middle. It's thicker upstairs here, thicker downstairs here. You see these rays are being bent away from the optical axis. You could imagine them coming from some point back here, some common point back here. This is the focal length of the diverging lens. And so you see this also on this little cartoon here, right? Parallel rays into the converging lens, they pass through a common point, the focal length. Parallel rays into the diverging lens, they appear to come from a common point, the focal length. It's even marked. It's even marked here. Okay, so that's the personality of a lens. We met focal lengths and focal points with mirrors, if you remember. There was a simple relationship between the mirror's focal length, focal point, and the radius of curvature of the mirror. So the focal length of the mirror was 1/2 the radius of curvature of the mirror. That's very simple. F equals R/2. Unfortunately, it's not as simple for lenses. It's not as simple for lenses if you think about it, because, well, mirrors, there's just one reflection. Now lenses, we got 2 refractions. Mirrors, there was just one surface with 1 radius of curvature. Now with lenses, we got the front and back surfaces and 2 radiuses of curvature. So there is, unfortunately, a more complicated relationship between the geometry of the lens, its curvatures of the front and back faces, and the focal length, compared to the geometry of a mirror, where you just have 1 radius of curvature and a focal length. This equation on this overhead is what's called the lens maker's equation. So I guess it was used by lens makers when they wanted to. If you go to a lens shop, what are you going to ask? You're going to ask for a certain focal length lens. Right? I want a 10 centimeter focal length converging lens. Or online, right? You're ordering, I want a 15 centimeter diverging lens. To build that lens, you've got to make a lens with curved front and back faces out of a certain material of a certain refractive index. And this lens maker equation tells you how to do that. So here's the focal length that we want to manufacture our length to be. And then here's how the focal length is related to the radius of curvatures at the front and back faces. These are the R1 and R2. This is where the first refraction occurs, R1. This is where the second refraction occurs, too. And then this N here, this is the material, the glass, or the ice that you've made the lens from. It depends on that, too. So all these three things, the radius of curvatures of the two faces and the material of the lens, go into the lens maker's formula and determine the focal length. Let me just make a couple of remarks about it. I made a couple of remarks down here. Look at that equation. I look at that equation. It looks extremely complicated to actually imagine it. But there are a few situations that you can imagine in that equation. Supposing we increase the refractive index. So, you know, we make a lens out of glass, 1.3 refractive index, and then I make a lens out of diamond, 2.6 refractive index. How's the focal length going to change? Well, comparing light going from air to glass compared to air to diamond, you're going to get a much, because of the higher refractive index in the diamond compared to the refractive index in the glass, it's going to bend the light a lot more. You're going to get a much smaller, shorter focal length because you're bending the light more. And this equation shows you that. If you increase n, so if we make n bigger and bigger and bigger as we go from glass to diamond, we're going to increase 1 over f, which means that we're decreasing f. We're making f shorter. We're making the thing converge more or diverge more. So that's embedded in this equation. Another thing that's embedded in that equation, supposing R1 and R2 were the same. You made the same radius of curvature of the front and back faces of the lens. In that case, you've basically just made a pane of glass. The thickness is the same everywhere. You don't have a thicker center and a thinner edge, or a thinner edge and a thicker center. If you make R1 and R2 the same, then the thickness of the lens is the same everywhere. It's not going to do anything. And this equation says that too. If R1 and R2 are the same, this cancels out. 1 over f is 0. That means f's infinitely big, which means that the lens does no converging, no diverging. So the equation does make some sense. Okay, let's look at some images formed. We're going to do converging lens, and then we'll do diverging lens, like we did converging mirror, diverging mirror. Okay. So this is a slide on the ray tracing for the converging lens, and then we'll do a slide on the equations for the converging lens, and then just show you a little demonstration. And then we'll do the same thing for the diverging lens, a slide on the ray tracing, a slide on the equations, and a demonstration. Okay, what am I doing here? So here's my converging lens. Remember, that's thicker in the middle, thinner at the edges, going to bend light towards the optical axis. Over here, almost fell off the screen, but here's the object in green. I labeled it object, and its position is the object position. And we're going to discover that here's the image. The image is in magenta. I labeled it I, and here's the image position Q. Through the center of the lens, this horizontal is the optical axis. Marked on the horizontal line is the focal length of the lens. I've marked it on both sides here. We normally do that for lenses. You'll see why. So that's the situation, and now I want to trace a few rays. And the rays I'm going to trace this time are, we've also got brother and sister or cousins here. We've got that same pair of rays that we use for the mirror, where you kind of go in parallel to the optical axis, or you come out parallel to the optical axis. And then on the other part of the path, you go in through the focal length, or you come out through the focal length. So we're going to draw those rays. So that's a pair of rays, and we're going to sketch those. And then there's also a ray. The easiest ray to draw is a ray that goes through the very center of the lens. And so that's a ray that you can always draw, and it's always easy to draw because it just goes straight through the center, undeflected. And so let's look at those rays. So in black, this is the easiest ray to draw, I mean, in my humble opinion. It's just a straight line that goes through the center of the mirror. And so here it is, heading away from the head of the object through the center of the mirror, undeflected. So that was easy. And then in blue and red, we got the cousins, right? One of them's in parallel, and one of them's in through the focal point, and one of them's coming out parallel, and one of them's coming out through focal point. So let's take a look at this. Here in blue is the one that goes in parallel to the optical axis, and it's going to be refracted, bent by the lens, and we know this is a converging lens, so it's going to be bent towards the optical axis, and specifically is bent towards the optical axis so that it heads through the focal point. And so this light ray that went in parallel was going to go through the focal point and head off here to the bottom right. The red ray is kind of the opposite. It heads in towards the lens, if we look at it, through the focal point, strikes the lens. Now, it's going to be bent so that it is converged towards the optical axis. So it was heading away from the optical axis. We're going to bend it more towards the optical axis. This ray is going to head out now parallel to the optical axis. So it was also converged. Both the red ray and the blue ray were converged as they passed through the converging lens. If you look at these three rays, they're both all three rays are heading off here towards the right. Here's my giant eye with my giant brain. I'm processing this information, and I'm saying, where do these three rays appear to come from? That's where the image is going to be. Well, I trace them back. The common point that these seem to come from is this point here. And so this is the location of the image. And so we found the location of the image. In fact, we found a bunch of properties of the image. We found its location on the back side of the lens. We found the fact that it's actually upside down. It's been inverted. The arrow is the opposite way up. It's below the optical axis. It started out above the optical axis, so the image has been inverted. And we found out also it's been minified. This image here is actually a little bit smaller than this object over here. So the height of this arrow and the height of this arrow are a little different. This one's a little smaller, this one's a little bigger. And so that's how you would construct a ray tracing diagram for the formation of an image of an object by a converging lens. Okay. So there's a pair of equations that help us compute the properties of the image. There's a lens equation that allows you to compute its location and what side of the lens it's on. And then there's a magnification equation that allows you to compute how much is magnified or minified, and also whether it's upright or inverted. And those are these two equations here. Look, this is like 3 equations now, because these are the same equations that work for the converging, diverging mirrors, and now we're finding that the same equations work for the converging, diverging lenses. And so that's very handy. You just have to remember that underneath this, in one case is a reflection in a single surface. Here there's two refractions, two surfaces. You have to be careful in both cases about whether things like the focal length are positive or negative, whether you've got a converging or a diverging lens or mirror, but the equations themselves are all the same. So for example, the lens equation, if you knew the focal length of the lens and the object position, you could calculate the image position. And then you could calculate the magnification of the image by basically the ratio, the negative ratio of the image position to the object position. Oh yeah, let's demonstrate. Let me show you at least a demonstration of a converging lens. I'm going to put the camera on. This is a converging lens. So if you look at this lens, it's thick in the middle, and it's thin at the edges. So that's the characteristic of a converging lens. It will bend light towards the optical axis. So I'm going to mount it here. And I'm going to shine light rays onto this lens. These are parallel light rays. And because they're parallel light rays striking the lens, they will be bent towards the focal length of this converging lens. Let me set the mood. And depending on where you're located, you may be able to see it clearer in the image up on the screen or on the board here. What you see is that those three incoming parallel light rays are indeed converged towards the optical axis, and they're actually converged through a common point, and that common point is the focal length of that lens. And so this is an example, an illustration of the bending of light through a lens and the focal length of the lens. This is another, I don't know if you can see it, but this is another converging lens. It too is thicker in the middle and thinner at the edges, but it has different radius of curvature and different thicknesses. So it'll also converge, but it'll have a different focal length. So kind of remember this point here. This is the focal length of this lens. And then we'll put its friend in here. And so now we're seeing for this second lens, its focal length. And this one's about 50% longer focal length. It converges a bit less. And so it has a longer focal length. It's somewhere out here now in this case. Anyway, that's an example of converging lenses. Let's do the same thing for, it's meant to be diverging lenses. Oh, that it? Yeah, here we are. Same thing for diverging lenses. So these are lenses that are going to bend the light rays away from the optical axis rather than towards the optical axis. So we're going to do exactly the same things. We're going to draw the rays. We're going to look at the equations. And we'll just look at a demonstration of a diverging lens. So here's the ray tracing. So let me stress, right, that the converging lens has a positive focal length when you use the equations. The diverging lens has a negative focal length. So they fundamentally differ in that distinction when you use the equations. Here's a diverging lens. It's thinner in the middle, it's thicker at the edges. Here's the optical axis through it, horizontal line. Here I've marked the focal length on the left and the right. Again, with lenses, you tend to use the focal points, we'll see, on the left and the right. With mirrors, we just used it either on the front face or on the back face, depending on whether it was converging or diverging mirrors. Here's the object in green again, labeled O, and object position P. Here's the image we're going to find, labeled I, and its image position is Q. And we're going to do the same business of tracing these three rays. This easiest ray that goes through the center of the lens, that's just a straight line, and then these cousins or brother and sister rays that head in parallel or head out parallel, and head in a way that involves the focal point, or out in a way that involves the focal point. Okay, so first of all, this black ray here goes right through the center and it's undeflected. That's obviously easy to draw that ray for a lens. The blue ray heads in parallel to the optical axis. And remember, this ray is going to be bent away from the optical axis. So I can't be drawing it going through this point, this focal point, because that would be bent towards the optical axis. I have to draw it as appearing to come from this focal point, to draw it as a diverging ray. So that's how we draw this diverging ray for this diverging lens. It's appearing to come from this point, not going through this point. So that was one of the cousins. And then the other one is the red ray here. So the red ray this red ray is drawn again in a way that diverges the ray. So the ray is going to be bent away from the optical axis. So you see it was going towards the optical axis, and then it's going to be bent away from the optical axis. To draw that, I've drawn that ray heading down here towards this focal point on this side of the lens, and then it's refracted, it's bent so that it heads parallel. So again, goes inwards towards a focal point, it's heading outwards parallel to the optical axis, and I've picked the focal point that will give us a diverging ray. And so that's how we draw the second diverging ray for the diverging lens. Again, over here on the far right, I got my giant eye, my giant brain, my giant processing of these rays that are coming out. The blue one, the red one, the black one down here, I'm thinking, where do they appear to come from? The common point they come from. That's where the image is going to be located. I trace the red one back, I trace the blue one back, I trace the black one back. They cross here, and that's where the image is located. We've seen here that we make a smaller image, a minified image, that is actually what we would call a virtual image. The light really isn't coming from here. It just appears to come from here. You know, this dashed line here is not a real light ray. This dashed line here in red, not a real light ray. It's just us, my brain, my mind, my eyes, retracing these rays to this common point. So this is a virtual image. Here are the equations that describe that image formation. Again, there's a lens equation and there's a magnification equation. The lens equation tells you that property of the image, which is where it's located, and also which side of the lens it's on. And then the magnification equation tells you, obviously how much bigger or smaller the image is. The magnification also tells you whether it's upright or inverted. So it tells you both those things. And again, these two equations are exactly the same equations for the converging lens. And they're exactly the same equations as for the converging and diverging mirrors. We just got to be careful about, in this case, converging lens has a negative focal length when we use when we use it for a diverging lens. Let me just show you a quick demonstration of a diverging lens. And then I'm just going to make a few remarks about the diverging lens and the converging lens. And then we'll look at some examples. Oh, I broke the lens. I'd be fired. Okay, here's a diverging lens. It's thin in the center, and it's thick on the outside. So that's the property of a diverging lens. It's going to bend the light rays away from the optical axis. And I'll mount that in here. And I'll put on the camera. Which is nowhere where I was going. Here it is. And the camera, to me at least, looks pretty useless. But let's see what happens when I set the mood. Oh, it's not so useless. What are we seeing here? We're seeing parallel light rays going in towards the diverging lens. So they're heading parallel to the optical axis. They strike the diverging lens, and they're bent away from the optical axis. And you can imagine, you can visualize where those rays heading off towards the right, where they appear to come from. They appear to come from some location off towards the left that's maybe 30, 40 centimeters away from the lens itself. That's how to imagine the focal length of this diverging lens. I got a second diverging lens. We can put that in. It will also diverge the rays. It's just that it has a different radius of curvature on the front and back faces, so it will diverge the rays by different amounts. And so this one actually diverges them by more. So the focal length of this diverging lens, because it's diverging more, the focal length will be it's negative. It'll be a smaller number. It's maybe this one's maybe something like 10 centimeters. So here we're seeing the properties, the characteristics, the personality of these lenses. Let me just mention, there's a lot of sign conventions with lenses, just like there's a lot of sign conventions for mirrors, about which side of the mirror or the lens is positive or negative for the object and for the image. The meanings of positive and negative focal lengths for the converging and the diverging lenses. Again, you'll get a table on test 3 that gives you the sign conventions for the lenses and the mirrors. So you don't have to remember this stuff. The other remark that I wanted to make was that if you remember there is an important distinction between converging, diverging mirrors. There is also an important distinction between converging and diverging lenses. Converging mirrors, converging lenses can both magnify and minify. So they can make things smaller and they can make things bigger, converging mirrors lenses. So they have this big world of things that they can do to an object in making an image. On the other hand, a diverging lens, a diverging mirror, they can only make the object, they can only make the objects, the image of the object smaller. They only minify. They do not magnify. So they have a more restricted world of manipulating the object when forming an image. So that is an important difference between converging, diverging, whether it's lenses or whether it's mirrors. Okay, we've got a couple of applications now. Oh, first one's a quiz. So this question asks you to compare a converging and a diverging lens, and to answer the question of whether they both can magnify, only the converging lens can magnify, or only the diverging lens can magnify. So I'll give you another minute or two to respond to that one, and then we'll get on with a numerical example. So again, diverging, converging lenses, diverging, converging mirrors have different possibilities in the images that they can form of objects. It's only converging mirrors and lenses that can magnify. A diverging mirror or a lens can never magnify, it can only minify. And so that's the answer to this question here. Okay, so here's a quantitative problem that involves a lens, and it involves, here's the object, and here's the a nickel, and here's the image of the object that we see in the lens. And so this is going to be an example where I'll both carry out the calculation. It'll be an example of the lens equation, magnification equation, and then we'll also draw some rays to understand what the equations are telling us. So a big example of ray tracing. So we're told in this particular question that we, for some reason, looked at a nickel in a magnifying glass, and the nickel appears, the object is twice the size, the image is twice the size of the object. So the nickel's diameter, the image's diameter, is twice the size of the true nickel, the object's diameter. We're told the magnification is 2. We're also told where the object is located. We're told that it's located at plus 2.84 centimeters. The plus means that it's located on the side of the lens where the light is coming from, and the 2.84 centimeters is just that distance from the center of the lens to the object. And based on that, we've got to find the focal length of our magnifying glass. So it's going to be interesting to see what the focal length of the magnifying glass is, see how we can magnify things with magnifying glasses. Okay, so in this problem, there were two quantities that we were told. There was two quantities that we know. There's the magnification, so I wrote that down, m equals +2. And there was the image position. That's p equals +2.84 centimeters. The plus for the magnification is telling us that the image is upright. The plus for the object position is saying that the object was located on the front side of the lens. So the signs have tell us something as well as the sizes do. Now, I want to find the image location. But actually, I've realized, if I just think about the lens equation. Start again. I want to find the focal length. I realized if I think about the lens equation, to find the focal length, you would need the object and the image position. And I don't know the image position. I know the object position. So first I'm actually going to figure out the image position. So this is what I said in my head. To find F, need Q. And to find Q, I'm going to use the fact that I know the magnification, and I know the magnification equation. So the magnification equation is that the magnification is minus Q over P. Or I could rearrange that Q, the image position, is minus P times N. And I know P and M, 2.84 centimeters and 2. And if I multiply 2.84 times 2, I got, and I got a minus sign in there, I'm going to get minus 5.68. Am I off the screen? No, not quite. No, but I'm leaning on this thing again, which I always do. You would think I'm back in elementary school the way I write on this thing. I don't know what it is. Anyway, minus 5.68 centimeters. It's not true, because in elementary school I could write, and suddenly now I can't. So we got the image position now, knowing the magnification. And so in my mind, the second step I said, if I want the focal length, now I've got width, P and Q, which I now have. I can find F. And I'm going to find F now with the lens equation. So 1 over F, the inverse of F, equals the sum of 1 over P and 1 over Q, the sum of those inverses, of those distances. If I fill in the numbers, I got 1 over 2.84 centimeters plus 1 over minus 5.68 centimeters. And I've already calculated that ahead of time, of course. 0.1, nope. Even despite that, I can't write it down. 176 inverse centimeters. That's the inverse of the focal length. And I take the inverse of that, I'm going to get F equals plus 5.68 centimeters. And so that's my calculation. I've figured out the focal length from the information I was given. Based on the information I was given, I first figured I was going to use the magnification equation to find the image position. Then once I found the image position, I was going to find the focal length of the lens. This is a positive focal length lens, so it has it's a converging lens. I already knew it had to be a positive focal length lens because we were magnifying the object to make the image. So it had to be positive, and we found it is positive. Now I'm going to attempt the impossible. I'm going to try and ray trace this image formation. Okay, so what I've drawn here is the vertical line. That's the lens. The horizontal line through the center is the optical axis. I'm going to mark on this the focal length that I've found. So over here on the left, over here on the right, labeled F, that's the focal length. That's the 5.68 centimeters. I'm going to sketch the object. So the object was located at what a mess. At 2.84 centimeters. On the light's going to come from the front face on the left towards the back face on the right. So it's located on the front face over here on the left, and it's 2.8 centimeters from the lens. This, remember, was about 5.7 centimeters from the lens. So there's my object. And now let's draw some light rays. Exciting bit. This is the light ray that's easy to draw. Even that one seemed hard. That's the one that goes straight through the center of the lens. So that was okay. Then we've got the brother and sister, the cousins. They're the ones that go in parallel, come out parallel, and involve the focal length. So let's draw those guys. The one that goes in parallel, is this one here, parallel to the optical axis, and then it's going to head off over here through the focal point. So that's one of the rays. The second one that's going to go in, involving the focal point, it can't go through this focal point. It's going to come from that focal point. It's going to be converged towards the optical axis and head out parallel. So notice all these rays are being converged. This one here is bent towards the optical axis because it went in parallel. And this one here, that was bent parallel, is also being converged. So those are the three rays that are emerging on the back side of the lens, out of the lens. And over here is going to be my giant eye. And my giant eye is going to look at these rays, reconstruct where they come from. Let's try and do that. This one up here is easy because it's parallel. This one's pretty easy. And this one I'll just pretend comes from there. And here they come from the same location. And this is the location of the image. And we see that this image, I'll label it I, is twice as big as the object. That's what we were told in the problem. It is located at 5.68 centimeters. Where is it? Somewhere. Yeah, here, on the front side of the lens. For image distance, if it's negative, it's on the front side. And so it's located here. It's a virtual upright image. It's the right way up, but the rays don't really come from there. They just appear to come from there. Anyway, I'm going to end there. We've talked about refraction by one surface and two surfaces. We talked about equations and ray tracing. We met the lens maker's equation, which tells you how the geometry of a lens is related to the focal length, and then the lens equation and magnification equation for finding the properties of image.